Okay, so let's take a look at your homework. Questions on page 200 and 203. Use the equations F delta T equals J. And then on Friday we had proved that F delta T equals M delta V. And we know M delta V is just delta P. So delta P is change in momentum. M delta V is mass times the change in velocity. F delta T, the force times the time, and J is the impulse. So the impulse is equal to the change in momentum. And we said you can pick any two of these four corners because they're all equal to each other. So which ones you pick depends on what you're being given in the question. Now the question's on page 200. I think they all deal with F delta T equals J. So number 30, a sledgehammer strikes a spike with an average force F of 2125 newtons down over a time interval of 0.0, so delta T, 0.0205 seconds. And the question wants to know what's the impulse. Okay, so it's just J equals F delta T. So 2125 newtons, 0.0205, and J is going to be equal to 43.56 newtons. And the impulse is always the same direction as the force, so that'll be down. Number 31. In a car crash, a car strikes a wall with an average force, so this is F, of 1.23 times 10 to the 7th newtons, and the force is going south. Over a time interval of 21 ms. ms is milliseconds. So 21 times 10 to the negative 3 seconds. Not in proper scientific notation, but milli is to the negative 3. And since it's not a final answer, we can cheat and write it like that. So it's asking for the impulse, so J equals F delta T. So 1.23 times 10 to the 7th newtons times, if you want to put it in correct scientific notation or move the decimal the right way, it would be 0.021 of a second. And when you do this, you get a J to be 258,300. So 258,000. Oh, and I just put the units on this J up here. It's newtons, but it's really Newton seconds. Newton seconds, and again the direction will be the same way as the force, so it'll experience the impulse also going south. So 258,300 Newton seconds. Number 32. Now in number 32 you need to actually use some info from number 31. So 32 says, in a car crash similar to the one described in problem 31, another car with the same mass and velocity as the first car experiences an impulse identical to the value you calculated in 31. So it's saying use the J from 31, okay? However, the second car was designed to crumple more slowly than the first. As a result, the duration of the interaction was 57.1 milliseconds. So this time the time is 57.1 ms, or 0.0571 seconds. Okay? And so it wants to know what will the force be if the time with the same experiencing the same impulse, but we've made the time longer because we've created the car so it crumples more slowly. It has a better crumple zone. So we're looking for F, so divide by T. So F will be equal to J over delta T. So your 258,300 Newton seconds divided by 0.0571 seconds. And when you do this, you're looking for a force, or you get a force of 4.52 times 10 to the 6 newtons. Now that's still pretty big, but look, it's almost a factor of 5. Where's the force? It's almost a factor, actually closer of 10, tinier than the original force. So by adding 0.036 of a second, which is really, really tiny, we've cut the force by a huge amount. I'm just going to figure it by how much. So 1.23 to the 7th divided by 4.52 to the 6th. So we've cut the force in, yeah, it's not a factor of 5. We've cut the force more than in half by about 2.5, which is huge if you're the person in the car. Okay? All right, the other page was page 203, and we're looking at questions 33, 34, and 35. So question 33, the velocity of a serve of some professional tennis players has been clocked at 43 meters per second. Okay, so that's a V, 43 meters per second. Assume horizontally, assume any vertical component is negligible. The mass of the ball. The mass of the ball is 0.06 kilograms, and it wants to know what's the impulse. So this V is a final. The initial speed of the tennis ball before you strike it is 0, and you're looking for J. And so if we look at our little square right here, we have an M, we have a VF and a VI, and we want J. So we'll use these two corners, and we'll say we know J is equal to M delta V over delta T. So J is equal to M VF minus VI. So J is equal to 0.06, and the VI goes to 0. It's 0.06 kilograms times 43 meters per second. And when you do, you get a J of 2.58 kilogram meters per second. And remember, that's the same as a Newton's second. All right, number 34 says a 0.035 kilograms, so that's our mass. 0.035 kilogram baseball is traveling 46 meters per second towards the batter. So VI, 46 meters per second towards. After the batter hits the ball, it's going 62 meters per second in the opposite direction. Our VF, 62 meters per second, and so that would be away. And the question wants to know the impulse. Again, you're looking for J. So we do exactly what we did up here, and we do J equals M delta V. So J equals M delta V, which is really, of course, M VF minus VI. Now, when you do this, my paper's moving around. Hand is in the way. Okay, there we go. When you do this, you have to be careful of directions. One is towards and one is away. So 0.35 kilograms. It doesn't matter which one you call positive, but you need to call one of them positive. So if we call towards positive, since that's the initial direction, then the final would go in as negative 62 meters per second minus, and the initial would go in as positive 46 meters per second. And so you would end up with 0.35 kilograms, and in the bracket, negative 108 meters per second squared. And when you do the math, you get a negative 37.8 kilogram meters per second. We said let's call the away up here negative when we called the towards positive. So that means this means away. Okay? All right, and the last one on this page says a student drops a 1.5 kilogram textbook from, so this is 35. So the mass is 1.5 kilograms, and they drop it from a height of 1.75